Okay, hello students. We'll continue with the discussion on complex numbers and analysis. This is part 3 of the module on complex analysis, and this is part of the course CHE 641 at IIT Kanpur. Okay, so just to briefly recap what we were doing in the last two modules, what we were trying to say was that we can find roots of a complex number even if you had z to the 1/4, where z is a complex number. We knew how to find this. For example, we would write z is equal to re to the I theta, and then we'll take z to the 4 as r to the 1/4, and then instead of e to the I theta we will write e to the I 2 pi n theta, where n is 0, 1, 2 and so on, right? And then right, and then we will try to put n, and then we will try to take then you'll divide by 4. This is right, and then we will try to see how many roots are there, and until they get repeated, you will suppose you have 1/4, you will have 4 roots, right? And if you have 1/2, you have 2 roots, and then the roots get repeated and so on. Okay, so now we'll continue with the same theme, but we'll look at one of the most important functions called logarithms of complex numbers. Okay, suppose you have a complex number z. Let's call w as ln z, okay, the function. Then z is e to the w. Okay, so if you have z1, z2, which is nothing but e to the w1 times e to the w2, this is e to the w1 plus w2. That means ln of z1, z2 is ln of e w1 plus w2, which is nothing but w1 plus w2, which is ln z1 plus ln z2. So ln of z1, z2 is ln z1 plus ln z2. Now, if w is written, see, w is ln z, natural logarithm of z, and z is written as r e to the I theta, right? Then w is ln of r e to the I theta is nothing but ln r plus ln of e to the I theta, right? This is ln r plus simply I theta. So this is ln z is w. Now we also know that you can write z is r e to the I theta plus 2 pi ki, where k is 0, 1, 2, 3, because if you go around 2 pi, you come back to the same point. So you can add, keep on adding 2 pi integral multiples of 2 pi I to the argument of a complex number, you will still get the same number. But if you take, okay, so let me erase this aspect. But if you take z to be this, and then ln z will be ln r plus I times theta plus 2 pi k, where k becomes 0, 1, 2, 3, so on up to infinity. Okay, so logarithm of a complex number z has in principle infinitely many values. Okay, so the value k for obtained by putting k equal to 0, so ln z is ln r plus I theta, is called the principal value of the logarithm. Okay, that is sometimes denoted as capital L n z. Okay, now in order to restrict ourselves to the principal value, we have to agree to keep the argument between 0 and 2 pi or minus pi to pi. Okay, this is something only then you will get a single valued expression. Otherwise ln can take infinitely many values. So let's take an example. Ln of minus 1. Okay, this is nothing but minus 1 can be written as 1 times e to the I pi plus 2 pi ki. Okay, that is minus 1. This is r, and then this is e to the I theta plus 2 pi ki. Okay, so ln of minus 1 is ln of 1, sorry, plus I pi plus 2 pi k. Now ln of 1 is 0. Okay, this is r. Ln of r is 0 in this case. So ln of minus 1 is nothing but I pi plus 2 pi k. For different values of k, this is 0, 1, 2 and so on, you will get I pi. Okay, and you will get I pi, you will get 3 I pi, 5 I pi and so on. Okay, so you will have multiple values of the function, right? And you can also have, it's not just you can also have plus or minus 2 pi k. You can also have other negative values of the argument also. Okay, now so this is something that we will have to remember, that you have functions such as square root which are 2 valued, we have cube root which are 3 valued. There are 3 values. Then you have nth root, you have n values of the complex function of n. If you say w is z to the half, it's 2 valued, 3 valued, n valued. But then if w is ln of z, it's actually infinitely many valued. Okay, now let's go to the next sheet, and now let's discuss how, so far we took a complex number, but then we raised it to, let's say, a real power or a fractional power. Now the question that we are going to raise is, can we have complex powers of complex numbers? That is, I have z and then I raise it to the power of w, which is another complex number. To understand how this is done, let's take the simple identity ln a to the b is b ln a, something that we know. So a to the b is nothing but exponential of b ln a. This is also something that we know. So let's take an example. Let's say we take I to the power minus 2i. Okay, can we raise this? So in order to do this, okay, first let's consider the ln of this. Ln, first what is ln of I? Because ln of a to the b is b ln a. Okay, so then we will say what is a to the b? It is e to the b ln a. So first we need ln a. So here a is basically I. So what is ln I? It is nothing but I times pi by 2 plus 2n pi. Okay, so I to the minus 2i, okay, which is a to the b. Okay, a is I, b is minus 2i, is e to the b ln a. This is what we are using here. Okay, use a is I, b is minus 2i. Okay, so a to the b becomes I to the minus 2i is e to the b, b is minus 2i ln a, which is ln I. Okay, this is nothing but, sorry about this, e to the minus 2i times ln I can be written as I pi by 2 plus 2n pi I. Okay, so if you simplify this, you will get e to the pi. See, 2 gets cancelled, I squared is minus 1, another minus is there which makes it plus or minus 4n pi. This is nothing but, this is I to the minus 2i is e to the pi, e to the 5 pi, e to the minus 3 pi and so on. Depending on which sign you use, you get multiple solutions. Okay, now I mentioned the idea of a branch point last module as well, but let's understand this in a bit more detail. See, if you want w is f of z to be single valued, that is, for each value of z there must be only one value of w. See, we already saw that even in the simplest case of square root, if you just traverse one full round in the z plane, you just travel one half in the w plane. This is z plane, this is w plane. So in order to cover the full w plane, you have to go around it twice. But if you go around it twice, the same point, okay, in the z plane will get mapped to two different points. In this particular case, w is z to the half, and in fact many different points in other powers, in fact to infinitely many points for logarithm. Okay, so it is important for us, we'll soon understand the notion of what is called an analytic function. An analytic function is one which has single valued. So one of the conditions for the analytic function on a complex plane is that the function must be single valued in the complex plane. Okay, so many complex functions are not single valued, they are multi-valued, but if suitable care is taken, properties of analytic function can be applied to these multi-valued functions, provided we make sure that we suppose you have z to the half, w z to the half. Okay, we make sure that, see, if you cross this line twice, if you increase theta from 0 all the way to 2 pi, then if you cross it twice, then you will get multiple values of z, so multiple values of w for the same value of z, right? So if you agree instead to not to cross this line, so that if theta goes from 0 all the way to 2 pi, approaches from below, but it doesn't cross 2 pi, then the function w will be single valued. Okay, now this point origin is called the branch point. Okay, and this line which we are agreeing not to cross in order to keep w single valued is called a branch cut. Okay, so this is a very useful idea in complex analysis, to keep things single valued. Okay, so for example, f of z is z to the half is r to the half e to the I theta by 2. It's also r to the half e to the I theta plus 2 pi upon 2. This is nothing but minus r to the half e to the I theta by 2. So there are two roots, right? So if z goes around full circle, okay, about the origin, okay, and then if you cross once again, then you will get the negative value of the same function. So the key thing is, what is the circle about? It is about the origin. So that is why the origin is called the branch point in this case. Sorry about this. That is why the origin is called the branch point. Okay, now it is useful or easier to use this as the branch cut, but in principle you could have chosen any ray from the origin and restrict theta within that only. So if you go around this ray and then you agree not to cross it again, then that also becomes a branch cut. This is also a valid branch cut. Usually you take the simplest branch cut that keeps your calculations simple. Okay, now let's return to the notion of analyticity of a function. This is a very, very important topic. Okay, suppose I have f of z. You have a function of z. This is the first time we are talking about functions of a complex number or a complex variable. Now the function itself, z, is of course x plus iy. Now the function itself will have, of course, a real part, right, plus I v times x of x and y. That's an imaginary part. Suppose I take the derivative of the function with respect to z, which is df dz. This is, in the usual sense, you will say limit delta z going to 0, f of z plus delta z minus f of z upon delta z. Okay. Now, the key question that we may have to worry about is delta z is not, z is in a plane. It's a complex plane. This is real of z. This is imaginary of z. Right? So you can approach delta, you can take delta z to 0 in many directions, because delta z is an increment in the complex number. So you can go to 0 in this manner, you can approach 0 in this manner, in infinitely many directions. Okay, so the function is analytic in a nutshell if this answer is independent of the manner in which this limit is taken. Let's take an example. F of z is x squared minus y squared plus I to xy. Okay. Now delta z is delta x plus I delta y. Okay. So because z is x plus iy, so if I take incremental changes, if I make incremental changes in delta x and delta y, then delta z will become just this, right? So f of z plus delta z minus f of z by delta z will become, instead of z plus delta z, I will put z plus x plus delta x plus I y plus delta y and so on, and then I expand. So if I, and then I subtract with f of z, I will get 2x plus I 2y plus delta x squared minus delta y squared plus 2I delta x delta y divided by delta x plus I delta y. Okay. Now, regardless of the manner in which you take delta x delta y 0, right, the order in which the limits are taken, for example, you may take delta x 0 first and then delta y 0, or delta y 0 first and delta x 0 and so on, then the last term, this term always is small and it vanishes in the limit of delta x delta y going to 0. So if f of z is z squared, this is basically the function we are looking at, z squared, then f prime of z is 2 times x plus iy, which is 2z. X plus iy is z. Okay, so this is differentiable for all finite values of z except when z goes to infinity. This is a well differentiable function. Okay, now let's consider a different function. Let's consider f of z is 2y plus ix. Okay, then we ask the question, what is limit delta z going to 0, f of z plus delta z minus I. This is f of z divided by delta z. This is nothing but, you will get limit delta x tending to 0, delta y tending to 0. That's the meaning of delta z tending to 0. 2 delta y plus I delta x upon delta x plus I delta y. Now let's take delta y as m delta x, okay, where m tells you the direction of approach. Then this limit, if you just substitute this, you will get 2m plus I by 1 plus im. Now this limit is dependent on m, so dependent on m. So it depends on what the value of m is, that is the direction of approach of delta z to 0. So this is not really differentiable, because you get different answers, okay, for depending on how you approach or how you take delta z 0. Okay, a function that is single valued and differentiable at all points in a domain R then it is said to be analytic in R. Said to be analytic or regular in R. Okay. A function may be analytic in a domain except at a finite number of points called singularities. Okay. So you may have a function, this is the plane, real z, imaginary z. Except for some isolated points where the function is singular, it may be regular everywhere else or differentiable and smooth everywhere else. An example is f of z is 1 by 1 minus z. Okay. So if you take f prime of z, okay, it's 1 by 1 minus z the whole square. Okay. And this is independent of the way in which delta z is taken to 0, provided z is not equal to 1. So this is an isolated singularity where the function is not analytic, but everywhere else it's analytic. Okay. So not all functions of a complex variable are analytic. Analytic functions are a very, very special class of functions. How do you find whether a given complex function is analytic or not? So there is a very famous set of conditions called the Cauchy-Riemann conditions or Cauchy-Riemann equations. When satisfied, will tell you what are the restrictions on the function f to be analytic. Okay. So let's take the limit L is equal to limit delta z going to 0, f of z plus delta z minus f of z by delta z. Okay. Now f of z plus delta z is nothing but u, f is u plus iv, remember the function is u plus iv, u of x plus delta x comma y plus delta y plus I v of x plus delta x comma y plus delta y. Okay, so the limit L will become limit delta x tending to 0, delta y tending to 0, right, u of x plus delta x, y plus delta y plus I v of x plus delta x, y plus delta y minus u of xy minus iv of xy whole upon delta x plus I delta y. Okay. Now let delta z be purely real, that is, it is equal to delta x. So delta z is delta x and delta y is 0. Then the limit L becomes partial u partial x plus I partial v partial x. Similarly, if delta z is purely imaginary, I delta y, then the limit L is 1 over I partial u partial y plus partial v partial y. Okay. Now if the function is analytic, then both these limits must be identical regardless of how you take here you are taking delta y 0, here you are taking delta x 0, that's implicit here, right? So if you equate these two equations, the real and imaginary parts, then you will get partial u partial x is partial v partial y, partial u partial y is minus partial v partial x. So these are the celebrated Cauchy-Riemann conditions for analyticity of a function. Okay, if the function satisfies Cauchy-Riemann equations, then the function is analytic. Okay. Now there is one more way of understanding analyticity. In complex numbers, a function is really a function of two variables, x and y. Instead of these two variables, we can go to z and z star. Z star is a complex conjugate of z. So x is, you can do a change of variable, half of z plus z star, and then y is half of z minus z star, and then substitute this back in the original function. Okay. Now partial f partial z star is partial f partial x partial z star plus partial f partial y partial z star. Okay. Now instead of f, I'll put u plus iv. So this is partial u partial x plus I partial v partial x times half plus partial u partial y plus I partial v partial y times minus 1 over 2i. Okay. Now partial f partial z star is nothing but half partial u partial x minus partial v partial y plus I by 2 partial v partial x plus partial u partial y. Okay. So if the Cauchy-Riemann equations are satisfied, then partial u partial x is partial v partial y, so this becomes 0, and then partial v partial x is minus partial u partial y if Cauchy-Riemann is satisfied. Okay. So that means that if the function is analytic, then it is independent of its complex conjugate. It's a function only of z. It's not a function of z. Z star should not be there. Okay. So the combination x y should appear only as x plus iy and not as x minus iy if you have an analytic function. Okay. So there's one more. So you have the Cauchy-Riemann equation: partial u partial x is partial v partial y, and then partial u partial y is minus partial v partial x. If you differentiate this with respect to let's say y, let's say x, and this with respect to y, and add, you will find that the right sides will cancel out. So you'll get partial squared u partial x squared plus partial squared u by partial y squared is 0. So the real part of an analytic function satisfies the Laplacian equation. Okay, such functions which satisfy the Laplacian equation are called harmonic functions. Okay, so it's not just the real part, even the imaginary part can be shown to satisfy the Laplace equation. Okay, so this is a very, very important idea, the notion of a harmonic function, and the fact that you have conditions for determining whether the function is analytic. If so, then the Cauchy-Riemann conditions should be satisfied. Okay, so let me go to a new slide. Okay, so now let's go back to singularities of analytic function. Okay, so let's say you have a function that satisfies the Cauchy-Riemann conditions in some domain, let's say D in the complex plane. Okay, then the question is, will the same function obey CR in the entire plane? Okay, the answer is it will obey, but except for some isolated points called singularities where the Cauchy-Riemann conditions are not satisfied, and therefore the function is not analytic at these points. So in such cases the function need not satisfy the Cauchy-Riemann equation. Okay, so at those isolated points, suppose you have f of z is 1 over z. Okay, this is nothing but x minus iy divided by x squared plus y squared after multiplying by x minus iy in the denominator and so on. So u of xy is x by x squared plus y squared, and v of xy is minus y by x squared plus y squared. Okay, so then you will find that u partial x is partial v partial y is equal to y squared minus x squared divided by x squared plus y squared whole to the half, and then similarly you can verify partial u partial y is minus partial v partial x. So the Cauchy-Riemann are satisfied, but at the origin the differentials approach different limits. they don't converge to the same value of the derivative. So we say that 1 over z has a singularity at z is equal to 0, which is the origin. Such a singularity is called a simple pole. Okay, such a singularity is called a simple pole. So a simple pole is of the form C1 by Z. Okay, more generally, at Z is equal to Z0, f of Z can be always written as R of Z0 by Z minus Z0 plus higher order terms. Okay, let's take an example, and this is called the residue of the function. Let's take an example, 1 over z plus I, 1 over z minus I, right? Then as z approaches I, f of z becomes 1 by 2i times 1 by z minus I. Okay. Now, the residue is obtained by taking f z going to I, z minus I times f of z. Okay. Now, this gives you 1 over 2i. This is the residue at z is equal to I. Okay. And you can easily follow this for the other pole as well, right? So, this poles of the form 1 over z minus z0 are called simple poles or a first order pole. Okay. So, if f of z goes as r of z0 by z minus z0 whole to the n, then this becomes an nth order pole. Okay. Now, so singularities are functions which are of the form 1 over z minus z0, but there is one, these are called regular singularities. Okay. But there is also something called an essential singularity. Okay. If a function has a pole of arbitrarily higher order that cannot be eliminated by multiplication of z minus z0 whole to the n, then it is called an essential singularity. So, f of z is e to the 1 over z, let's say. Let's consider that. Now, this is nothing but summation over n. If you just expand this, 1 by z to the n factorial. Okay. So, this means that this has an essential singularity at the origin. So, we have three types of singularities. One are poles, then you have branch points, and then we have essential singularity. Okay. Now, we'll stop here at this point, and then we will continue. I'm sorry about this, and then we'll continue in the next lecture or next module.